Hi, and welcome to another recording. In this one, we are going to be going through the answers to the problems relating to scientific notation and exponents. Very quickly, the first one, the square root of 49 times 10 to the minus 18. If you do this on your calculator, you will get 7 times 10 to the minus 9. But I want to convince you that there might be another way to look at this. If we think about 49 times 10 to the minus 18, we recognize 49 as being the square of 7. And 10 to the minus 18, if we ask what times itself gets us 10 to the minus 18, we return to the rules of scientific notation and how to deal with exponents, and we see that when we add the exponents together, minus 9 and minus 9 would add up to 10 to the minus 18. So in this case, we could divide up this problem and say, what's the square of 49? What's the square of 10 to the minus 18? And we would get 7 times 10 to the minus 9. So you can start looking for these things that make sense. Start hanging different pieces of information off of things you already know. Next problem. Arrange the following quantities in order of increasing volume. So we want the smallest volume first. But before we begin this problem, I want to ask you a different question. So write these two numbers down. Which would you rather have, 300 or 80? And if you say, well, I don't know, that's good. Now, suppose that I said 300 pennies or 80 quarters. Now, which would you rather have? And I hope what this makes the point to you is that until I give you the units that we're dealing with, the magnitude of the number doesn't tell us anything. 300 is a bigger number than 80. But 300 pennies is a smaller amount of money than 80 quarters. So it is the thing that comes after the number that is just as important or more important in setting the magnitude of the number that we're talking about and what it's worth or how big it is as the number itself. So when we look at 10 liters, okay, so you might imagine how big 10 liters is. Again, there's about 4 liters to a gallon. So this would be about 2.5 gallons. So picture a gallon of milk, 2 gallons of milk, and then an extra half gallon of milk. That's about 10 liters, give or take. Now here we have 0.1 megaliters. Now, you probably don't deal with megaliters every day, so this is an exercise in imagining these things. So here I'm just going to write 10 liters, 0.1 megaliters. Now, I always like to, as I've said before, get rid of that mega and let's convert everything to liters, because then at least that way we've got a fair fight in trying to decide the magnitude of these things. If we get everything on a liter scale, then we can actually compare the magnitudes out in front. Well, another way of writing 0.1 times 10 to the 6th, if you type that into your calculator will probably return 1 times 10 to the 5th liters. This is an enormous number, right? 10,000 liters. That's a lot of liters. That's a lot of milk. 20 centiliters. Well, how big is a centa? Remember, centa is times 10 to the minus 2. So I'm going to rewrite this as 20 times 10 to the minus 2. And then we still have the liters there. So again, we've done our little extraction bit. We plucked out the C and inserted the times 10 to the minus 2. Another way of writing this would simply be 0.20, where we swing the decimal. So we have 0.2 liters. So not even a liter, a fraction of a liter. And 100 milliliters. So this would be 100 times 10 to the minus 3 liters. Now 100 is a bigger number than 20. So you might initially be fooled that, hey, that 100 is bigger. But when we actually swing the decimal place, this becomes 0.1 liters. This was 0.2 liters. So in fact, this is twice as big as that. So even though 100 is a bigger number than 20, 0.1 liters is a smaller number than 0.2 liters. So in ascending order of size, we'd have 0.1 liters or the 100 milliliters, followed by 0.2 liters, which is the 20 centiliters, 0.1 megaliters, 10 liters, and then 1 times 10 to the 5th liters, or the 0.1 megaliters would be the largest. So here again, even though 0.1 is smaller than 10, 0.1 megaliters is a lot bigger than 10 liters. Next one, converting 7.5 times 10 to the negative 7 milligrams to picograms. I have a hint here. I grant you could look up on Google, how do you convert milligrams to picograms? On an exam, you will not be able to use Google. Okay. So better to know these things. I always say in my class, if I were stranded on a desert island, I don't have Google, what do? I go through meters. Right? So I'm going to first grams in this case. I'm going to go through grams. So 7.56 times 10 to the minus 7 milligrams. Then I'm going to say, hey, I know that there are 1,000 milligrams in a single gram. If I were to do that, if I were to take this number, divide by 1,000, I now have an answer in grams. I'm not asked for an answer in grams, I'm asked for an answer in picograms. But now I can do a conversion because I know the conversion pico is 10 to the minus 12. So there are 10 to the minus 12 picograms in a gram. They are very small. You could also choose to write this as 1 picogram. 10 to the positive 12 picograms in a gram. There have to be a lot of picograms in a gram. So 10 to the positive 12 in a 10 to the positive 12 picograms in a gram. You could write this 10 to the minus 12, very small number of grams in a picogram. So now if we work with scientific notation, we'd have 7.56. We have a 1 and a 1 and a 1. So we still have 7.56. We essentially have 10 to the minus 7 divided by another 1,000. Or we can think of this as times 10 to the minus 3 times 10 to the positive 12. Well, what do we do with exponents? We add them together. So we have minus 7 and minus 3 is minus 10 plus 12. We'd end up with 756 times 10 squared picograms because the grams would cancel. We get 7.56 times 10 squared picograms, or 756 picograms. Next problem, Naomi Osaka, who's a tennis phenom, serves a tennis ball with a speed of 53.6 meters per second. I think that's pretty accurate. I looked that up one time. A tennis ball weighs 58.5 grams. I looked that up too. Energy is equal to 1/2 mv squared. Now, this is an exercise in units. Notice we are being asked for the units in energy in joules. And we are told a joule is a kilogram times meter squared times seconds to the minus 2, or per second squared. So the first thing I'm going to do is drop in the numbers. We have the mass of the tennis ball is 58.5 grams. And then the velocity is 53.6 meters per second, and that number gets squared. Right? So we drop in the velocity here, and then we have to carry over the squared. A lot of people get careless and they forget about the squared. If we look at units alone, we would have grams times meters. The meters get squared, and the seconds get squared. So notice whatever we do on our calculator now, our unit's going to be grams times meters squared, seconds squared. Our hint here says a joule is a kilogram meter squared, second squared. So right away, before we even touch a calculator, we know that at some point in this problem, we're going to have to convert grams into kilograms. Now, we could choose to do it right now and get this grams into milligrams and insert that into our problem. I'm going to choose to wait and do it at the end. So if I take 53.6 squared, multiply that by 58.5, divide the answer by 2. If I've done things correctly, I get E is equal to 84,034. And then we have our units, grams, meters squared, seconds squared. Again, please get in the habit of writing the units as you write the numbers too. Don't guess at the units at the end. If you guess at the units at the end, here you probably just hope that they'd come out to be kilograms, and we've already convinced ourselves that that's not the case. So that turns out to be this. Now we've got to do our conversion into kilograms. There are 1,000 grams in a kilogram. A kilogram is a big mass, so there must be a lot of the little grams to make up 1 kilogram. So we divide that number by 1,000, so we get 84.034. Grams now cancel. Kilograms, meter squared, second squared. But then we could say, well, 1 kilogram meter squared over second squared is 1 joule. So here we bring back our complex fraction analysis. We have kilograms meter squared in the numerator of this number. They cancel kilograms meter squared in the numerator of the denominator. We have second squared in the denominator here, and we have reciprocal 1 over second squared, which we saw come up as second squared. So if they came up as second squared, we'd have second squared in the numerator canceling second squared in the denominator. Or we could just view this in the whole denominator as second squared over 1 times this collection. And there we see also that the second squareds cancel. So we are left now with joules. So we can confidently write this as 84, rounded to 3 sig figs because we're limited there. The 84.0 joules would be our answer. So there's a big difference. If I say 84 joules versus 84,000 joules, that's a big difference. It might not seem like it on a chemistry test, but if I call you and say, hey, you just won $84,000 versus you just won $84, that's a big difference. And it's a big difference on an energy scale too. How many micrograms are in a gram? Micrograms, very, very, very small, micro, tiny. So there must be a lot of them in a gram. And in fact, there are 10 to the 6th micrograms in 1 gram. That's the equivalent. If you have 1,000,000 micrograms, you would have a gram. How many grams are in a microgram? Well, it must be a fraction of a gram. It turns out to be 0.00001 grams is 1 microgram, or in other words, 1 times 10 to the minus 6 grams is equal to a microgram. So notice we can write these conversions in either direction, but depending on how we write them, we either get a positive exponent or a negative exponent. So practice problems, adopt a methodology where you always get it right. For me, most of the time, it's easiest to think about 10 to the minus 6 as being that little micro. So I would say 10 to the minus 6 grams as 1 microgram. Next one, what is a femtosecond and how many femtoseconds are in an actual second and how many femtoseconds are in a minute, an hour, or a 15-week semester? Well, femto is 10 to the minus 15. So 1 femtosecond is 10 to the minus 15 seconds. Very short amount of time. It's about the time scale of a chemical reaction, bonds breaking and bonds forming, and we can actually watch chemical reactions happen on this time scale. There are lasers that allow us to see things with 10 to the minus 15 second resolution. Very cool. So now the next question is how many femtoseconds are in a minute? Well, let's start with our thing that only has 1 unit. 1 minute only has 1 unit. We know that there are 60 seconds in a minute. Notice I'm setting this up so that the minutes cancel. And I've chosen a conversion that gets me into seconds because I know I eventually want to get into femtoseconds. And we just found out that we want femtoseconds up here. So 10 to the minus 15 seconds is 1 femtosecond. We could also write this as 10 to the 15th femtoseconds per second. Notice that that's going to turn out the same way because 10 to the minus 15 in the denominator flips up as 10 to the positive 15 in the numerator. And if you take this and you do 60 times 1 times 10 to the 15, 15, you get 60 times 10 to the 15 femtoseconds. That's a lot of femtoseconds in a minute, or 6 times 10 to the 16th femtoseconds is equal to 1 minute. So we could express it as 6 or 60, but when we do that, we have to swing the decimal over a little bit. Similarly, we can say 1 hour. For the next one, how many femtoseconds are in an hour? 1 hour. There are 60 minutes in an hour. There are 60 seconds in a minute. There are 10 to the 15 femtoseconds in a second. So notice I'm convincing myself again, all of my units are going to cancel. I'm now converting 1 hour into femtoseconds. And if you just take 60 times 60, you get 3,600. So very easily without a calculator, you could report this as 3,600 times 10 to the 15th. And then, I'm sorry, yeah, 36, yeah. And then you could swing that over 3 more times and you get 3.6 times 10 to the 18th. Yeah. And that would equal 1 hour. Doubted myself there for a second. Something still doesn't feel right about that. So if I've made an error, please don't hesitate to contact me. I would appreciate it. And I can correct this video and the associated answer key. Next one down, 15-week semester. So if we start with 15 weeks, we know that there are 7 days in a week. 1 day has 24 hours. Now at this point, because we've just worked out 1 hour is 36 times 10 to the 18th femtoseconds. Sorry, I should have the units there. We could just go ahead and use that conversion, but again, stranded on a desert island, if we hadn't figured that one out before, we could then go through 1 hour has 60 minutes. 1 minute has 60 seconds. And there are 10 to the 15th femtoseconds in a second. And again, I'll just emphasize, this is really the equivalent of the number 1. 7 days is equal to 1 week. When we divide something by itself, this is 1. So we're not changing 15 weeks. We are simply expressing it in a different way. Rather than saying 15 weeks, if we do all this math and we take 15 times 7 times 24 times 60 times 60 times 1 times 10 to the 15th, you get 9.07 times 10 to the 21st femtoseconds would be how long a semester is going to take. That's a lot of femtoseconds. That's a 9 followed by 21 zeros. But a femtosecond is very, very, very small, so they go past very, very, very quickly. Every second that goes by, 10 to the 15th femtoseconds have gone by. Okay. So hopefully those all make sense. Quickly go through the last couple here. Hi, in the problem coming up, somebody pointed out to me that I made a mistake and I used 10 to the 6th as the conversion factor for gigameters to meters, when in fact it's 10 to the 9th. So what this means in all of the 4 following conversions is each one of my answers is 3 orders of magnitude too large. So for example, if the answer is 10 to the minus 6 as the answer, then it really should be 10 to the minus 9th as the answer. I have corrected this in the file that is uploaded that shows the written solutions to these, but as the next problem unfolds, just bear in mind that it should be 10 to the 9th as the conversion factor, not 10 to the 6th. Use that in the calculations and you will get the correct answers, each one being 3 orders of magnitude smaller than what I've shown coming up. Sorry about that. I hope it didn't cause any confusion. My apologies. Make mistakes, but I try to correct them when I can. So I appreciate someone telling me about this, and I hope it doesn't cause any confusion on your part. Thanks. How many gigameters in a millimeter? So giga, again, capital G, stands for 10 to the positive 6 millimeters, little m, 10 to the minus 3 meters. So we could say 1 millimeter, since we're asking how many gigameters are in 1 millimeter. I'm going to say that there are 1,000 millimeters in a meter. And now that I've done that, I now have a unit in terms of meters. If I were to stop here and calculate 1 divided by 1,000, I'd have my answer in meters. And now I can also add in that there are 10 to the 6th, 10 to the 6th meters in a gigameter. A giga is a lot. A gigabyte hard drive has 1,000,000 bytes in it. So if we do that math, we take 1 divided by 1,000 divided by 10 to the 6th. That is equal to 1 times 10 to the minus 9 gigameters. Next one, 1 picometer. Now, picometer to millimeter or to gigameter, I don't know those conversions between pico and giga. So like I said up here, I'm going to go through meters again. 1 picometer, there are 10 to the 12th picometers in a meter. And then we have 10 to the 6th meters in a gigameter. And if you do that, you'd have 10 to the positive 18 in the denominator. It would come up as 10 to the negative 18 in the numerator. So think about that, 10 to the 12th times 10 to the 6th. We add the exponents, you'd get 10 to the positive 18th. And then because it's in the denominator here, we saw in earlier videos, when you flip it up, it would become negative. Picometer cancels picometer, meter cancels meters. We are left with units of gigameters. Next one, 1 kilometer. Converted into gigameters, 1 kilometer has 1,000 meters. And there are 10 to the 6th meters in a gigameter. So now we'd have 10 to the 3rd divided by 10 to the 6th, essentially. 10 to the 3rd divided by 10 to the 6th. Kilometers cancels kilometers, meters cancels meters. We are going to be left with an answer in gigameters. 10 to the 6th divided by, 10 to the 3rd divided by 10 to the 6th is 10 to the negative 3rd. 3 minus 6 would be the exponent. 1 terameter. There are 10 to the 12th meters in a terameter. Terameters cancel. 10 to the 6th meters in a gigameter. And that's going to be 10 to the 12th divided by 10 to the 6th. So we end up with 10 to the 6th gigameters. There are 1,000,000 terameters in a gigameter. So if you have a 1 gigabyte hard drive versus a 1 terabyte hard drive, the 1 terabyte hard drive is 1,000,000 times bigger in memory than the gigabyte hard drive. Square centimeters into, how many square micrometers are in a square centimeter? So here is 1 square centimeter. We start with the thing that has 1 unit. And now we're going to layer on some conversions. There are 100 centimeters in a meter. Notice I'm going to again go through meters because I know the conversions between centa, milli, pico, micro, nano, all those to meters. I'm not going to remember what micro converts to femto. There's just too many of the different conversions, because then you'd have to memorize micro to femto, micro to pico, micro to nano. But if I just know all of them relative to the base unit, meter or gram or meter or gram or second, we can always convert back to that. Now notice this was squared, so we have to square the conversion term. And then the next one, we want to get into micrometers. So 1 meter has 10 to the 6th micrometers. And we would square that. And centimeters squared is going to cancel the centimeter squared. Meters squared is going to cancel the meter squared. But now we can't forget to square the terms. So here we really have 1 over 100 times 1 over 100 times 10 to the 6th times 10 to the 6th. 1 over 100 is 10 to the minus 2. This is 10 to the minus 2 times 10 to the 6th times 10 to the 6th. When we multiply all this, exponents would add together. So we'd have minus 2 plus minus 2 is minus 4. Plus 6 is a positive 2. Plus another 6 is a positive 8. Or another way to look at it is 12 minus 4. So we'd have exponent of 10 to the 8th. And in terms of units, meters squared would cancel the meter squared, and the only unit standing is microns squared. So we'd have 10 to the 8th microns squared. Last one. I'm sorry, not the last one. How many square micrometers are in 15 square centimeters? Same problem as above. 15 centimeters squared times 100 centimeters per meter squared times 10 to the 6th micrometers in a meter. And again, we need to square that conversion term because our units are squared here. We're not squaring the 15. This is an area. It is, somebody saying, hey, this is, a 7 by 2.1 square area. So when you do that multiplication, you'd get like 14.7. Rounding up, you'd get 15 square centimeters because it's an area. And now we have to do the conversions. We said that if we convert this side to meters and this side to meters, we'd be introducing the same conversion factor twice. So it gets embedded twice, gets squared. And this would turn out to be the same thing in terms of we'd have 15 times 1 over 100 times 1 over 100 times 10 to the 6th times 10 to the 6th. And we just get 15 times 10 to the 8 microns squared. Last one down. How many picoseconds are in 240 megaminutes? Now, I asked, should this answer be small or big before we begin? Megaminute, mega, really big, lots of minutes, a huge minute. Kind of almost makes no sense, but a huge minute. 10 to the 6th minute. That's going to have a lot of seconds, even if we're just seconds. But now we're talking about picoseconds. Picoseconds are really, really small, smaller than regular seconds. So if we have a really, really big number and we chunk it up into really, 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 really small pieces, we should have a ton of those small pieces. So we should expect a really big number. So we start with 250 megaminutes. A megaminute would have 10 to the 6th regular minutes in it. We know that there are 60 seconds in a regular minute, and 1 second contains 10 to the 12th picoseconds. That's the definition of pico. Or you could have 10 to the minus 12 seconds is 1 picosecond up there if you'd like. And now you take 240 multiplied by 60 multiplied by 1 times 10 to the minus 6, or 10 to the positive 6 rather. If you like writing the 1 times 10 to the 12th, you can do that as well because you're multiplying by 1, so you're not changing the number. So 240 times 10 to the 6th times 60 times 10 to the 12th. Notice 10 to the 12th, 10 to the 6th is going to be 10 to the 18th. We've got another factor of 10 here, that's 10 to the 19th. And then we have 2 more orders of magnitude here, so 2021 as a bare minimum. And in fact, when we do that, we get 1.44 times 10 to the 22 picoseconds. Mega minutes cancels mega minutes. Minutes cancels minutes. Seconds cancels seconds. We are left with an answer in picoseconds. And then the 1.4 and the extra place comes from the fact that 2.4 times 6 would give us 12, which is bigger than 10, so it shoves the decimal place one more place over. So we can anticipate or know that that 10 to the 22nd is a good number. And we're confident that we've got things right, both in terms of the magnitude of the number and in terms of the units, because all the units canceled. Last problem, just a little refresher here. X, y to the fourth over 1 over xy. We multiply the denominator by xy, multiply the numerator by xy, so we're really multiplying top and bottom by the same thing. Xy cancels in the denominator, that makes the denominator 1, that's why we do it. Now up here in the numerator, we'd essentially have x times y, which is x squared times y, and then that would be over y to the fourth, but we see that the y's can cancel, so we cancel one of the y's, so we get x squared over y cubed over 1, or x squared over y cubed. And again, by the time the semester begins or mid-semester, I would hope that you could look at a problem like this and just say, oh, okay, I'm going to get rid of that, multiply by xy. One of these y's is going to cancel. That's going to be x squared over y cubed, and do it a little bit more efficiently. If you're still doing this, that's fine at this point, but start trying to see if you can't convince yourselves of skipping a few steps, knowing that if you're multiplying the denominator by its reciprocal, it's going to go away, so you don't need to write those ones. I'm doing it to show how some students have to think their way through this, but I'd like students to get to this because it'll make you a faster, more efficient problem solver in solving more complex problems where this is just a small part of the bigger problem. So again, I hope these help, and I look forward to hearing from you. If I've made some mistakes, please don't hesitate to call me out on it. I would appreciate it. In fact, because I don't like disseminating incorrect information. My pen is even tired tonight. So my email address again is mark.vitha, V-I-T-H-A, at drake.edu. Please contact me if you have questions, and have a good rest of your day. Thank you.